First, let's find the area of the original triangle using Huron's formula. The semi-perimeter is 27, so we'll calculate the square of the area, and so the area of our original triangle is 90. Now for n equals 1, we're going to find B1 according to the problem statement on segment AB0. C1 is going to be on segment AC0. So let's redraw this triangle with B1 and C1. According to the problem statement, our original triangle AB0, C0 is going to be similar to triangle B0, C1, C0, and this is similar to AB1, C1. So we have a congruent angle here, and these angles at C0 and C1 are also congruent. So let's sketch these three similar triangles. This length over here is 17 again. We'll find the ratio of the side length of this triangle in the middle, B0, C0, to the corresponding side on our original triangle, AC0. That's 17 over 25. We'll go ahead and call this R for simplicity. Since we're interested in triangle areas, the ratio of the area of the triangle in the center, B0, C1, C0, to our original triangle is the square of the ratio of the corresponding side lengths, or R squared. So solving for the area of triangle B0, C1, C0, this is R squared times the area of the original triangle, and we found that that area was 90, so this is 90 R squared. Let's see if we can do the same thing with this triangle on the right. Let's let X be the distance from A to C1, so X is over here. This means the distance from C1 to C0 is 25 minus X. So I'll mark these here. Let's see if we can figure out what X is using these first two triangles. The ratio of side length B0, C0 to C1, C0 is the same as this first triangle. So we'll substitute the side lengths. 17 over 25 minus X. This is 25 over 17. We can solve for X here. So now we'll use this value of X to compare the corresponding side lengths of our third triangle and our original triangle. This is the ratio AC1 to AC0, or X over 25, and then I'll substitute this value of X. I'll write this as 1 minus the square of 17 over 25, which is 1 minus R squared. Since this is the ratio of our corresponding side lengths of our third and first triangle, the ratio of the areas of these triangles is going to be the square of this ratio. So 1 minus R squared squared. And then solving for this triangle AB1, C1, and then we have our original triangle has an area of 90. We're interested in repeating this process and summing the areas of this remaining triangle. The first one here is triangle B0, C1, B1. We'll calculate that by taking our original triangle and subtracting the two triangles that happen to be similar. Again, the area of our original triangle is 90. We have this area over here, 90 R squared, and then this last triangle is 90 times the square of 1 minus R squared. We'll factor out the 90 from all of these terms. The next triangle in our sum is triangle B1, C2, B2. To calculate that, we'll take triangle A, B1, C1 and multiply it by this same factor. Here again is A, B1, C1. This is B2, C2, and that's the triangle that we're adding to the sum. We already have an expression for A, B1, C1. That was this over here, 90 times the square of 1 minus R squared. The product of this first and last factor was the area of this triangle up here. So I can write this as 1 minus R squared squared times the area of triangle B0, C1, B1. And this process repeats for subsequent triangles that we're adding to our area sum. Each subsequent one will be multiplied by this factor from the previous triangle. So the sum of the areas of these triangles, this will be an infinite geometric series with the starting value equal to the area of our first triangle, and the common ratio in this series is this factor over here. Our formula for the sum of an infinite geometric series is A over 1 minus R, where R is the common ratio. I'll plug in for A and 1 minus R. I'll factor out 1 minus R squared from these two terms inside the parentheses and combine like terms. It'll be easier to see how we can cancel out some more factors if we let Y be equal to 1 minus R squared. And so R squared is 1 minus Y, and we'll make that substitution here. And then the denominator, it's easier to see that we have a difference of squares factorization. So we can cancel out 1 minus Y in our numerator and denominator. And then I'll go ahead and substitute back in 1 minus r squared for y. Now we're ready to plug back in. R is equal to 17 over 25. We'll start by getting rid of the fractions by multiplying by 25 squared over 25 squared. This might be easier if we write our numerator and denominator in terms of the difference of squares factorization. I'll pull out one of these 25 squareds. In this problem, we're only interested in the denominator, so I want to see what factors are going to cancel out. So I'll just leave my numerator unmultiplied and in terms of its prime factors. So here's 90. 25 minus 17 is 8. And then over here I have 42, which I'll write as 6 times 7. In the denominator I have 625 plus these same factors from the numerator. We'll continue to evaluate the denominator. This denominator is 961. We can quickly check to see that this is not a multiple of 2, 3, 5, or 7, so there are no factors in common, and Q is equal to 961. If you'd like me to solve any other math contest problems, please leave them in the comments.